Welcome, this is Mr. Brewer here. I'd like to give you some guidance on how to solve stoichiometry problems using a method that I like to call the proportion method. Before we begin, why don't we review some of the language that would help us understand a little bit about the background of stoichiometry. Stoichiometry is really just a way to compare how reactants, usually found on the left side of the reaction arrow in a chemical equation, compare to quantities of products, or how reactants also compare to other reactants. We need to recall that quantity means many things and often relates to a concept in chemistry that we refer to as mole. Mole can actually have three different meanings when we refer to chemical quantities or amounts. Mole can relate to something that we call the molar mass of a chemical, described by its formula, the molar volume of a chemical, described by 22.4 liters, as long as that chemical is a gas and it's at standard temperature and pressure. Mole can also relate to the number of particles, which is Avogadro's number, 6.02 times 10 to the 23rd particles. We therefore see that stoichiometry really relates four different kinds of quantity: mole, molar mass, gas volume at standard temperature and pressure, or number of particles. Before stoichiometry problems can be solved, one must take notice of something important that relates to stoichiometry, and that would be something called mole ratio. Mole ratio is always defined or described by the coefficients, the numbers written in front of each chemical as a reactant or a product. You see the numbers circled in purple here. Each of these represent mole quantity amounts or ratios. These ratios allow us to relate the quantities of any reactant to other reactants or any reactant to any product. We see in this chemical equation there is a ratio of 2 to 25 on the reactant side and 16 to 18 on the product side. Again, these represent mole amounts. Mole amounts are always revealed by what we call the balanced equation. The balanced equation is all of the information revealing quantity and which chemicals participate in a reaction. You can see it circled in red here below. To begin a stoichiometry problem, one must read the information provided. What one should be reading for is looking for critical information. The critical information would be to determine what is the given quantity of chemical that was provided in the information, and what type of amount or what chemical are we interested in, or quantity that we are turning it into to arrive at an answer. I always like to refer to this as the given and the desired information in the problem. Therefore, you're reading for both a given amount and a desired amount. Keep in mind that the given chemical has a different identity than the desired chemical. It may also have a different kind of quantity. Recall that quantity comes in four different types: mole, gas volume at standard temperature and pressure, mass, or number of particles. Reading the problem below, we can see that the given quantity is 1,280 liters of carbon dioxide gas. This is the amount that we know that we have of a chemical. The desired quantity is in the form of a question. It asks for what mass of octane liquid would be needed if we were going to produce 1,280 liters of carbon dioxide gas. The proportion method that I would like to model will always use two fractions. The first fraction will simply be the given information from the words in the numerator and the desired information from the words in the denominator. The given quantity is now written as the numerator of the first fraction, 1,280 liters of CO2. The desired quantity is always the unknown amount. Therefore, I like to refer to it as X. Be sure to tell what type of quantity and which chemical the desired quantity refers to. In this case, it refers to what mass of octane. Therefore, we're looking for C8H18 in mass amount, which means in grams. So it's X grams of C8H18 as our denominator. Now we simply make a second fraction equal to the first fraction that we've provided. The second fraction will have both the same quantities and chemical identities in both the numerator and the denominator. Therefore, we'll transfer the same information over to the left side. Liter of CO2 and gram of C8H18, or octane. Now you have to recall your mole information in terms of what amounts are equal to 1 mole. If we had 1 mole of any gas at standard temperature and pressure, the volume of that gas would always be 22.4 liters. Likewise, the mass of octane, or C8H18, would be equal to 114.26 grams. We have to recall that these are only the amounts equal to 1 mole of CO2 or 1 mole of C8H18. And looking at the balanced equation, the two chemicals that we're interested in ratio are not 1 to 1 mole. There's actually a 2 to 16 mole ratio as indicated by the coefficients. We must always account for this mole ratio when using stoichiometry in the second fraction of our setup. Therefore, we'll use these numbers as multipliers in the corresponding positions for each. Therefore, 16 becomes the multiplier for CO2, and 2 becomes the multiplier for octane, or C8H18. Let's rewrite this in some space so it's more readable for you. Once we've applied the mole ratios, we can now use simple algebraic methods for solving. When solving a proportion, cross-multiplying is always one of the more efficient ways to solve. Therefore, we will multiply x times 16 times 22.4. This gives us 358.4x. Now we will cross-multiply 1,280 times 2 times 114.26. This gives us 292,505.6. Now we simply wish to solve for x by isolating x. In order to do this, we simply divide each side of the equation by 358.4. The rounded value that this reveals is 816. Let's keep in mind what x actually represented. X represented an amount of grams of octane, or C8H18, which we must represent our answer as. Therefore, our answer, revealed in the circle below, 816 grams of octane. Let's try a few more examples of stoichiometry. One thing you must keep in mind is that no two stoichiometry problems will ever really be identical, because there may be different chemical equations that they are described by, there may be different kinds of quantities that they're relating to. Again, could either be mole, a gas volume, a mass, or a number of particles. But the basic setup using the proportion method is always the same. Let's read the problem and look for both the given and the desired quantities and chemicals that we're interested in. The given quantity, 468 grams of magnesium oxide, is provided as the numerical amount. Therefore, we look for the numerical amount and assume that to be the given quantity. The desired quantity is in the form of a question. Therefore, it asks, what mass of magnesium nitride? Magnesium nitride would be a chemical that has both magnesium and nitrogen in it. Therefore, our desired chemical would be identified with the symbols Mg3N2, while the given quantity, 468 grams of magnesium oxide, would be given or represented by the chemical symbols MgO. Now that we've identified both the given and the desired chemicals, let's begin to set up this stoichiometry problem using the proportion method. I like to put the given amount again in the numerator of the first fraction. The given amount, again, is provided by the words 468 grams of magnesium oxide. The desired amount, again, I always like to represent as x, because it's an unknown. And what it's asking us to find out is x mass, which is in grams, of the chemical known as magnesium nitride, represented by the symbols Mg3 and 2. Now we set up the second fraction in a proportion, which matches the first fraction in terms of the kind of quantity and the chemicals that we're interested in. Therefore, we copy the labels from the left side and duplicate them on the right side for both numerator and denominator. Once we have that set up, then we look for the amount that is equal to 1 mole for each of the quantities of the second fraction on the right side. We'd be looking for the quantity or the molar mass of MgL, which is the amount equal to 1 mole of MgL. Factoring in a quantity of 1 Mg, or magnesium, and 1 oxygen, we arrive at a molar mass of 40.31 grams. Likewise, factoring in a quantity of 3 Mgs and 2 Ns for the denominator, we arrive at a molar mass of 100.95 grams for magnesium nitride, or Mg3N2. Recall, these are the quantities that are only equal to 1 mole, and our balanced equation below may reveal an amount or a ratio that is not 1 mole, but some higher amount. Therefore, we need to read or interpret the balanced equation. Looking at the coefficient for MgO, we see the value 3. Therefore, the multiplier for the numerator is 3 moles. Looking at the coefficient for Mg3N2, we see that there is no coefficient. In this circumstance, there is an assumed 1 for the coefficient value. Although there is no coefficient listed, it represents a quantity of 1 mole. We now have the problem set up and are ready to algebraically begin to solve. We simply cross-multiply to begin solving. Therefore, 3 times x times 40.31. This reveals an amount of 120.93x. Now we cross-multiply 468 times 1 times 100.95. This reveals an amount of 47,244.6. Next, we solve for x by isolating for x, which means we divide each side of the equation by 120.93. In doing this, our rounded amount to 3 significant figures is 391. Again, recall what x represents. In this case, x represents the number of grams of magnesium nitride, or Mg3N2. Therefore, we must identify it with the correct labels. Let's begin by reading the problem and looking for the given quantity. In this case, the given quantity is 13.6 moles of dinitrogen pentoxide, which would be the symbols N2O5. The desired quantity is asking for the number of moles of nitrogen dioxide, which would be the quantity or the symbols NO2. Let's set up the first fraction, which is always listed as the given quantity over the desired quantity. Our given quantity, 13.6 moles of dinitrogen pentoxide, or N2O5, is written as the numerator. Again, our denominator is x, which is an unknown, and we must list the kind of quantity. It asks for a mole amount, and the chemical we're interested in this case is nitrogen dioxide, represented by the symbols NO2. Recall the fraction on the right side should duplicate the symbols that you see on the left side. Therefore, it will have the kind of quantity, mole, along with the type of chemical, or which chemical, N2O5. Again, the type of quantity, mole, along with the chemical we're identifying, NO2. In this case, this is a special form, or a unique form of stoichiometry, where we are only really interested in mole quantity. Mole quantity relationships tend to be more simplistic in terms of solving a stoichiometry relationship for. This is because the molar mass, the amount equal to 1 mole in mass in grams, is not related to this problem, nor is a volume related to the problem. Simple mole amounts are the only thing that we really need to worry about. Recall that mole amounts in a balanced equation are always represented by the coefficients. Therefore, to solve this, we simply need to plug in coefficients that come from the balanced equation. The coefficient for dinitrogen pentoxide, or N2O5, happens to be 2. So let's insert it where it belongs, on the top with N2O5. The coefficient for NO2 belongs on the bottom, which happens to be a 4. We have the problem set up. Now all we simply need to do is use our algebra to solve for the unknown. Recall we cross multiply to solve for the unknown. 2 times x becomes 2x, and 13.6 times 4 becomes 54.4. Now to solve for x, we simply divide each side by 2, and x is now represented by 27.2. Recall what x represents. Our unknown, written in red, again, is moles, but it's moles of the chemical known as nitrogen dioxide, or NO2. I hope that you found this lesson useful. While there are other methods for solving stoichiometry problems, this is a nice organized method that can give you an option. If you check my resources, you may find on my YouTube channel other ways to solve stoichiometry problems, but this is one method that some students might relate to because of similarity, perhaps related to their mathematical instruction they've received. Thanks for checking in. Until the next time.